Dear students, very good afternoon, Canberra, Australia. Good morning, Sri Lanka. Welcome to the Astro Week Astronomy IMC International Lecture Series and Online Certificate Program 2025. Today we are going to talking about the challenges of Mars sample return mission. For these discussions, we have invited to the very special person, Professor Jonathan Clarke, CEO at Mars Society Australia, and former senior lecturer at Research School of Earth Science, Australian National University. Let me highlight very intro about the today's our guest speaker, Professor Jonathan Clarke, complete his BSc degree in geology from University of Tasmania in 1981 and PhD from Flinders University in Adelaide in 1988. He spent 13 years in resource exploration industry, working in field-based coal, oil, groundwater, gold, diamond, and copper exploration projects across the Australia, Chile, Philippines. He has been engaged in geoscience education program at University of Tasmania, Flinders, and at the Australian National University. Jonathan has spent 14 years working for Geoscience Australia in marine survey, salinity, groundwater, and pre-competitive minerals explorations field. John has had a lifelong interest in space explorations and the planetary science. In 2001, he joined Mars Society Australia, become a president in 2012, a position he has held to the present. John has taken a part in 6 Mars analogue expeditions in Australia and one each to the Ladakh, India, and New Zealand. He has also participated in 3 rotations at the Mars Desert Research Station MDRS in Utah, including the Devon Islands at the Flashline Arctic Research Stations in Canadian Arctic. Jonathan has been an associate member of the Australian Centre of Astrobiology since 2004 and online instructor in astrobiology at Swinburne University 2017 to 2020, and also adjunct faculty member at the Amity Centre of Excellence of Astrobiology since 2020. He currently working on Mars EVA suits for Human Aerospace Pty Limited. John has contributed more than 100 peer-reviewed publications in geoscience, analogue research, and astrobiology. Professor Jonathan Clarke is a panel member of the Astronomy IMC since 2021. With that being said, I would like to invite this talented and the glorious scientist to address Astronomy IMC International Platform. Professor Jonathan Clarke, now it's your time. You can get started.
Thank you very much for that effusive welcome. It's a great pleasure to be able to talk to the class here today and follow on from previous talks given at other times. So if I can get my presentation up and running, I'll be talking about the challenges of Mars sample return. Why are we interested in Mars sample return? Why is it important, and how we might go about doing it. First of all, very quick review. When it comes to successful missions, we already have quite a lot of data from Mars. There have been 9 flyby missions, spacecraft that have flown past the planet, 16 successful orbiters, including India's Mars orbiter mission, 5 successful landers, 6 rovers, and 1 helicopter, which flew from the Perseverance mission in 2020. So with all this data, why is it important to actually get samples from Mars? And the reason is quite simple. It's that terrestrial laboratories, earthbound laboratories, will be vastly better at analyzing samples than any robotic laboratory that we can send to Mars. They will be more accurate, they'll be more sensitive. The samples can be investigated by a great more teams and methods which are much more precise than those available on Mars. And so, for example, here we have in that sort of gold-colored box in front of those two people wearing the isolation suits in the top right of your screen, we have the SAM instrument on the Curiosity rover. It's about 1 meter square, yeah? In the bottom picture is an enormous instrument here in Australia, in Melbourne, called a synchrotron. It's one instrument, but it can do a vast range of different kinds of highly accurate, very precise measurements. And that sort of contrast is always going to exist while we have to analyze samples on Mars remotely or by bringing them back on Earth. So I hope that this gives you the impression of how much better it is to have the samples to hand than to look at them remotely. The second thing to remember is, because of this, meteorites, rocks that have fallen from the sky, are the poor person's space probe. It costs many billions of US dollars to send a spacecraft to Mars or other bodies in the solar system to bring samples back. But samples are falling from the sky all the time. None of them normally as big as this one, which is the largest known meteorite in Namibia in Southwest Africa. But even the smallest meteorite can provide us tremendous insight into the composition and history of the bodies from which they come. So here we have an example of different types of meteorites. On the left we have the asteroid Bennu, from which we actually have samples returned to Earth by a US mission. We have simple meteorites that have not differentiated. We call these chondrites, so called because they have little round balls in them called chondrules. And these are a feature of meteorites that have not undergone what we call differentiation. What do I mean by that? I'll explain. So in the middle, we have several other meteorite families. We have up the top, we have eucrites. These are essentially basalt, like you'd find on the Deccan Plateau in India, for example. We have howardites, which are a gabbro or a peridotite, similar to what you find in some very large igneous intrusions. We have iron meteorites on the bottom, made up primarily of iron, an iron-nickel alloy, and we have stony irons, which are quite rare, and they are a mixture of rock, silicate rock, and metal, hence their name. And these represent different parts, samples from different parts of differentiated bodies, like the Earth. The eucrites represent the crust, the howardites represent the mantle, the stony irons represent the transition zone between the core and the mantle of bodies out there, and the irons represent the core. So not only are these different types of meteorites samples of different types of asteroids and other bodies out there in the solar system, they also provide us a window into the inside of our own planet. And by the way, we also find meteorites on Mars. This was one that was photographed on Mars by the Curiosity rover. You can see it's actually a nickel-iron meteorite, an iron meteorite, and it's just sitting there on the ground of Mars quite happily. and it probably weighs several hundred kilograms. But just as we find meteorites on Mars, we also find meteorites from Mars. And here is one from the Roberts Massif in Antarctica that was picked up on the glacial ice and returned to a meteorite collection. Antarctica has proved to be a very good place to look for meteorites. As you can imagine, inland in Antarctica, everything is white, so any rocks on the surface are really going to stand out. And it's been found that where the ice flows in particular locations, meteorites can become concentrated, and you can hunt them down and bring them back for study. So how do we find out that these meteorites came from Mars, as opposed to, say, the moon or some asteroid? Well, the story is quite interesting. Back in the 1970s, we knew there were a small group of 9 achondritic meteorites. That is, they lack these little round balls, little round spheres that indicate they are primitive meteorites. They were fragments of igneous rocks that had once been molten, like basalt, and they belonged to 3 separate classes. 3 shergottites, or a bit over 3 shergottites, 6 shergottites, 3 narcolites, and you'll see the unique Chazagi meteorite. And they were recognized that their chemistry was very similar, and they all came from the same body. If you wonder why they got such funny names, these meteorite families, meteorite classes, are named after the places where they were first found. So the narcolite meteorite, for example, was named after Narkala in Egypt, where the first example occurred. Now, we didn't know where they came from. We know they came from the same place. They contained iron oxide, rust, essentially. And some people said, well, yeah, Mars is a red planet. It's got rust on its surface, iron oxide on its surface. So maybe these meteorites came from Mars. Beyond that, we couldn't say. Until in the 1980s, when people melted up small samples of these meteorites and looked at the gases that they gave off. These are the noble gases and other gases, krypton, xenon, neon, argon, nitrogen, and carbon dioxide. And they looked at the how these plotted on a graph and compared their composition with that of the Martian atmosphere, which had been measured by the Viking landers. And lo and behold, they fell on a straight line. And those of you familiar with statistics, of course, will know that a straight line plot of data is very good and indicates a very strong correlation. So since about 1983 to 1985, after a bit of discussion, it is generally accepted that these meteorites come from Mars. How do they get to Earth? Well, Mars is covered in craters. Some of these are very large. And by mathematical modeling, people were able to determine that any crater that was formed by an impact on the surface that was more than 10 kilometers across ejected enough material at a high enough velocity to escape from Mars's gravity and travel through the solar system. And a tiny fraction of that material would end up on Earth as meteorites. So, as of earlier this year, this is what we have. There are 208 Mars meteorites known. We find a few more every year. So by the end of this year, it'll probably be 210, maybe even more than that. The vast majority of them are chazagnites, a small number, shergottites. A smaller number of those are narcolites, and a very small number are chasognites, ultramafic meteorites, and things from the actual surface of Mars, like regolith, which is essentially soil, or impact melted glass from other impact craters. And here's what they look like. These have been cut, and you look at their faces, and they're just basalt, or dolerite, or gabbo, or peridotite, rocks that you'd get from the Deccan Plateau, and you wouldn't really look twice at them if you found them on a drive through the Deccan region. What distinguishes them is their gas chemistry, which tells us they're not from Earth, but they're from Mars. Here's some more. These are more unusual meteorites. The regolith breccia from northwest Africa, and you actually see it's made up of pieces of other rock that have been glued together. The Narkla dunite meteorite, which came from much deeper in the in Mars, excavated from a deeper depth from the Martian mantle. Chassigny is another example, and this very strange meteorite, Allen Hills 84001, the oldest Mars meteorite we've found, that also contains evidence of being modified by liquid water, and it contains some structures that for a number of years some people thought indicated that they were biological in origin, along with traces of organic matter. The jury is still out on that, although most people think that these are not actually signs of Martian life. But because of that, people find these meteorites extremely interesting because they can give us clues onto the early history of Mars and its habitability. How old are these meteorites? We can date these rocks radiometrically, just like we do on Earth, and we can date two things. We can date how old those rocks are, and you can see here that some of them are over 4.5 billion years old. Allen Hills 84001, for example, there, but most of them are actually less than 1 billion years old. And these are various shergottites down in the bottom left. The second thing we can date is the shock event that ejected them from Mars and sent them on their journey to Earth. And the majority of these are quite young. The oldest one is about 20 million years ago. Most of them are 5 million years ago or even more recent. And this makes sense. If meteorites from Mars end up on Earth, it's more likely we're going to find meteorites that were thrown off Mars relatively recently geologically, as opposed to much further back in geological time, because meteorites are gradually swept up by the planets in their orbits. So what have we learned from Mars meteorites? Well, the first thing it confirms is that material is transferred between planets. Not only are bits of asteroid descending from the sky onto Earth, but also fragments of Mars. Incidentally, we also know from studying lunar samples that fragments from Earth have ended up on the Moon, and we can infer that it's even possible that some may have ended up on Mars as well. We can confirm what we suspect from other information on Mars, from satellite imagery, from rovers crawling around on the surface, that Mars has a long history of volcanic activity and water activity, aqueous activity. We can confirm that there are organic molecules present on the surface of Mars and also beneath its surface. Not only have we confirmed these, the meteorite ages in particular provide constraints, limits, if you like, of the rate at which this process goes on. Constraints on the age and composition of the surface, on the chemistry of rocks, of water on Mars, the atmosphere, and how the crust, mantle, and core of Mars have evolved. And of course, there are controversies. Geologists have three hands. On one hand, some say this; on the other hand, some say that; and on the third hand, others say a third thing. So there is still debate over whether or not there really is evidence of life in Martian meteorites. There is some date over the formation ages. So this slide I showed there represents the consensus view, the view of most people who worked on Mars meteorites, but there are a minority who dispute these. And the last thing that we have found from Mars meteorites, and this has only been in the last couple of years, and very much to my surprise, is we can now link at least some of the Martian meteorites to specific locations on Mars, which I never would have thought was possible. And so, for example, shergottites, these are the young basaltic meteorites that make up the majority of Mars meteorites, probably came from Tooting crater, not that far from Olympus Mons, the biggest volcano on Mars. The Black Beauty meteorite, the regolith breccia, probably came from down here in Karratha crater, from some of the edge of the southern highlands of Mars. So here is Karratha crater on Mars. There's a picture of Black Beauty, which you see is made up on many different types of rock, all cemented together to form a breccia. By looking at these different pieces, they concluded that the initial crust formed a large crater, and a large crater was formed, the initial crust, which ejected these rocks, and then from the Karratha crater, some was ejected from the Martian surface, to one piece of which formed a Black Beauty meteorite. Now, they could do that because it had a unique composition, a unique chemical composition, a unique age composition, and a unique physical composition from its magnetic properties. And out of 90 million craters scanned by artificial intelligence, Karratha is the only one that formed a match to these properties of Black Beauty. Tooting crater, or the shergottites, 88% of known Mars meteorites, almost all of which are less than 500,000 years old. And the Tharsis volcanic province, that includes Olympus Mons, is the most likely area they came from, because that is a large area of young volcanoes. And Tooting crater is a match for composition and age, not only age of rocks, but age of formation. And also there may be a small number from another crater which doesn't have a name, but just that number there, 09-000015. So, if we've got all these meteorites, over 200 meteorites from Mars, on the surface of the Earth, and getting more every year, and if we can learn so much from them, why bother spending lots and lots of money sending spacecraft to Mars to bring back samples? And there's several reasons. First of all, the samples we get from Mars as meteorites are contaminated. They have been modified from their original case. First of all, they've been shocked as they have been ejected from Mars. They've undergone changes in space. They've been exposed to heat and cold. They've been bombarded by the solar wind. and this changes their composition in subtle ways. As meteorites, they're ploughed through the atmosphere at a velocity of many kilometers a second. This has caused the melting of the exterior and, of course, the loss of a lot of the volatiles, a lot of the trace gases that can occur in meteorites, and whose composition is of great interest to many scientists. And lastly, they've been sitting on the surface of Mars the surface of the Earth for long periods of time, from anything from a few days to many hundreds of years. They're weathered, they've been hydrated, they've been contained water, there've been mineral and chemical changes, and terrestrial biota has started to infiltrate into their interior. So while we can learn lots about Mars from these meteorites, there are still problematic aspects of studying them. Secondly, context matters. What do I mean by context? Let's say I go to your house and I bring a pizza for people to eat. And you ask me, where does that pizza come from? And my answer will make a great deal of difference as to whether or not you will share that pizza with me. If I say it comes from a restaurant, a pizza restaurant, say, you'll probably eat it. If I say, oh, I just picked it up off the road, where someone had dropped it, you'd probably turn me away, unless perhaps you were very, very hungry. Context matters. So knowing where a sample comes from on Mars is really important, and can tell us a lot more than if it's just a random sample. And meteorites are random samples. The third reason why the third reason why we have problems with Mars meteorites is that they are not very diverse. We've got 208 Mars meteorites. Of these, all but 2 are of igneous rocks that were once lava or molten rock deep inside the Earth. Only 2 samples come from the surface, either as melt rock from an impact, or as, like Black Beauty, of surface material regolith cemented together. Now, of these, nearly all are shergottites, and almost all less than 600 million years old, which is only a very, very small proportion of the age of the Martian surface. Only 2 meteorites we know are more than 4 billion years old, close to the formation of Mars. Of those, one is a whole meteorite, our old friend Allen Hills 84001. The other one is a small fragment in another old friend of ours, Black Beauty. So when we send spacecraft to Mars, when we send robots to Mars to collect samples, we want to look for samples that fill in the gaps. Yeah, so we want to have old rocks, more than 3.5 billion years old. We want to have unconsolidated regolith, scooped up sand from the surface of Mars. We want to have igneous rocks that aren't mafic. We want sediments. We want highly altered, weathered rocks, those around fossil hot springs. And we want samples from deeper below the surface. And lastly, we want rocks that contain volatile elements, samples of the atmosphere and the water. And we have actually started that process of collection. This is the NASA Perseverance rover, which is trundling around the surface of Mars as we speak. And it is collecting samples of material from the surface of Mars for return to Earth. Now, if you return things to Earth, right, we want to make sure we don't bring some nasty Martian bug back to Earth. And this is, of course, beloved by Hollywood movie makers. This dreadful movie Life from about 7 years ago. Don't bother watching it if you haven't. It's a lot of rubbish. But nonetheless, there is a concern that we could bring back some new disease from Mars if there was life in it. And this is embodied in a piece of international law called the Outer Space Treaty of 1967, which nearly all the countries on Earth have signed. And Article 9 states that basically countries that explore outer space and organizations belonging to countries that explore outer space, including the moon and other bodies, will explore them in a way to avoid the contamination of other planets and also adverse changes to Earth from bringing material back. And so that was in 1967. At that stage, we had one probe on the moon, landed safely on the moon, the Soviet Luna 9 on the left there, and the following year we had the Surveyor spacecraft, the first US one to land. Since then, those procedures and principles have evolved, and we now have, and this applies to all countries, doesn't matter whether you're China or India or the US or Russia or European or Zimbabwe, any samples that are brought back from Mars, first of all, have to be collected from a sterilized spacecraft, and the samples must be brought back in a way where the contact chain between Mars and Earth is broken until the samples are in a laboratory. And there's a whole lot of review process to make sure this happens. And we've done a lot of these sample return missions, not from Mars, but from other missions. For example, Luna 20, a Soviet mission in 1972, brought back lunar samples. American Stardust missions, which brought back samples from a comet in 2006. Hayabusa, the Japanese mission, in 2020 from an asteroid. OSIRIS-REx, a NASA mission, 2023, which brought back samples from another asteroid. And most really, the Zhanghe 6 mission, the Chinese one, that brought back samples from the far side of the moon, the first ones we had from that part of the moon. But these are all from bodies, asteroids, the moon, where there is no life, and we don't have to worry too much about breaking the chain of contact. Let's just make sure that the material isn't contaminated when it lands back on Earth. By breaking the chain of contact, we've got to make sure that the sample, when it's transferred into the spacecraft to bring it back to Earth, that no part that has been on the surface of the spacecraft that collected the sample it gets in contact with the spacecraft that brings it back to Earth, and the part of that spacecraft that contacts the Earth environment. So this is what the US from NASA has devised to do that for its return samples from the Perseverance rover. You have the sample, which are in a container. These fit inside a secondary container, which then is put into a third container on the orbiting spacecraft, which of course has never been on Mars. And the whole thing is encased inside a landing body that enters through the Earth's atmosphere like a shuttlecock from badminton. Doesn't use a parachute. It's designed to withstand hard impact and protects through multiple layers of protection the sample from contacting Earth until it's put into an appropriate laboratory. And by an appropriate laboratory, the first samples, at least until we've decided they are safe, will go through a biosafety level 4 laboratory. I mean, this is serious stuff. This is where people handle things like Ebola virus and smallpox viruses and anthrax in laboratories on Earth. There's only a few around the world. Very, very complex laboratories with multiple levels of protection. I would be very, very surprised to see if they find life in these samples, and I'll be even more surprised if they turn out to be hazardous. And that's a subject for conversation afterwards. So getting back to how we're going about collecting these samples. Here we go, the Perseverance rover on Mars that carried that little helicopter I mentioned earlier. It's exploring an ancient river delta on Mars. It started out landing out on the floor of the crater. It climbed up onto the data, up the river channel, and is now on the rim of the crater down in this area where hopefully you can see my arrow down in the bottom left of that picture. And what samples is it collecting? It's collected over 20 samples so far, 25, included the atmosphere. It's going to use some witness tubes, which are just tubes that do not collect any sample, but they provide a way of checking for any contamination that the other samples have received. It's collected old rocks over 3.5 billion years from the rim of the crater. It's collected sand. It's collected sediments from the delta, and it's collected heavily altered, highly weathered rocks also from the rim of the crater. So far, it has not found any non-mafic igneous rocks or collected any deep cores, simply because it can't collect any deep cores. It only collects small things about the size of a pen, as you can see from that picture there. And this was the original plan. The rover would collect the samples, it would deposit them on the surface. A fetch rover would pick up the samples and take them to the return lander, which would fire off a small rocket into Earth or into orbit and return them to Earth, into Mars orbit, which would then, the Mars orbiting spacecraft would bring them back to Earth. Unfortunately, that is all off the table now. President Trump has been elected, and he would like to cut spending in a whole range of areas, including Mars sample return. So whether these samples ever get returned to Earth is at the moment uncertain. Fortunately, we're not dependent on the US. The Chinese space program is very advanced and doing very well, and they also have a Mars sample return plan. In 3 years' time, they'll send a spacecraft to Mars on 2 spacecraft. One is the lander, one is the Earth return spacecraft, relying on the heritage from their Zhurong Mars rover mission and from the Zhang'e 5 and 6 Mars lunar sample return missions, and bring them back to Earth. And by the time they do that, they would also had a asteroid sample return mission to gain experience on. And what will we find? We'll probably find old rocks, 3.5 billion years old again. They'll collect cores, a deep core, over 1 meter, probably 2 meters deep, including soils, possibly sediments, and loose rocks. They'll have an arm that picks up loose rocks and puts them in the sample collection device. Whether they'll find non-mafic rocks there or not, we don't know. And these are the areas on Mars that it is looked at, all just north of the equator. Probably one of those green dots is where they will come down. And there's just a sketch of the orbiting of the spacecraft mission profile. So by the end of July 2031, all being well, we'll have samples from Mars. Now, whether it's the US mission or the Chinese mission, there won't be a lot of material, about half a kilogram. So they'll have to be handled very, very carefully. There's a spacecraft design, the landers in the aeroshell, the lander itself, and the orbiter. Lastly, when we send people to Mars, they will be bringing samples back. And the advantages of sending people to Mars is that they will be able to cover enormous distances, not just a few kilometres or a few tens of kilometres like robotic rovers, but they'll traverse hundreds or even thousands of kilometres during their stay on the surface. They'll be able to document hundreds of sites, not just tens of sites. They will have enormous scientific payloads to characterise the rocks on the surface so we can bring back the best ones. Not just a few kilos of instrumentation, but tons. They'll bring back hundreds of kilos, not hundreds of grams, from diverse sites. People are, all of us here, we're fast, we're flexible, we're adaptable, we're intelligent and creative. All the things that robots aren't. And lastly, we go to Mars for the bigger picture. What does this all mean for the human condition? Is it possible for humans to live on Mars long term? And only having people on Mars can we assess these big questions, whether or not we could ever live there permanently. Of course, the downside of it, human missions are expensive, they're complex, people get all funny over risk to crew, and it will take several decades to implement. But Mars sample return using rovers or deep drills is also a multi-decadal project. So we're doing that sort of thing anyway. And this is just a chart showing the advantages of crewed missions over robotic missions in terms of the scientific output, using the moon as an example. So we have the number of papers published from all the unmanned missions to the moon at the time this paper was written, back in 2012, which was perhaps 500 odd papers, compared to the number of papers published from the Apollo missions, which only spent 14 days on the moon in total, but they had almost 3,000 papers published from that length of time. So yes, robotic missions are great, but really we want people on the ground, boots on the ground, exploring the surface of the moon, surface of Mars in this case, to get the maximum benefit. So yeah, that's the same thing again. So in summary, current exploration, we've got orbiters, landers, rovers, helicopters, they're great, but we need samples to really understand Mars. We already have Mars samples, meteorites, but Mars sample return is better than meteorites because they're localized, contextualized, they're new materials, and that in the future, when we send people to Mars, we'll have even better samples to study and to understand. So, questions?
Thank you very much for the very informative sessions to our Professor Jonathan Clarke. It's a very interesting sessions about the challenges of the Mars sample return. Dear students, now it's time to have a Q&A sessions. If you have any further questions, make sure to raise your hand. John, I have a couple of questions because I'm also interested in your presentation that you have done on today. So simply, if it is any kind of a meteor coming from the Mars, so what kind of dating methods that we should do? What are the most convenient?
Well, essentially most of the dating methods that we use for terrestrial rocks, so potassium argon, argon, uranium lead dating. Because when it comes down to them being rocks, these are mostly basaltic rocks, just like we have on Earth, and all the techniques that we use here will work on them. For shock dating, it's usually argon. We can also, third thing we can date is also how long they've been in space before they landed on Earth, and actually more accurately, how long have they been sitting on the surface of Earth since they're in space. and that is using what we call cosmogenic isotopes like aluminium-26, beryllium-3, and so on. And again, these are the same tools that we use to date, say, erosion rates on Earth. So we look at a rock on the surface of the Earth and how long has it been sitting there. We can use cosmogenic isotopes to work out that length of time.
I see. Thank you very much for the answer. And same time, is there any possibilities to survive or any kind of preservations coming with those meteorites? So while those meteorites trying to our atmospheric entry, is there any possibilities to survival?
Well, that's an interesting question that to yet we don't have the answer. It could take a few million years for something to travel from Mars to Earth. It is possible with a large meteorite for bacteria to remain viable in a state of hibernation inside a large meteorite, more than a meter across, for that length of time. So it is possible if there was a very small chance, but it's not impossible that had there been life on Earth, it's been brought here. Perhaps more interestingly, it's also possible that a large asteroid hitting the Earth would eject rocks that would become meteorites on Mars and perhaps take Earth bacteria to Mars. As I said, there is a transfer of material between planets. So I think sometimes people can get a little bit too anxious over planetary protection because material is moving between planets all the time. Yeah,
I think that would be very interesting. As you said, sometimes there could be some impact of our planet Earth, and same time Earth bacteria could be just heading to the space and come back years of years later. That sounds much interesting. And also, what exactly happened on Mars? Why there is no such a life indication? So, life that we are expecting, I don't think we have been discovered over there. And also, some of scientists have been just mentioned there are some fossils and other things, but I don't think in scientific way. Is there any such a records?
There is nothing conclusive. There are some interesting hints that there may have been life on Mars, or possibly life on Mars in the past, perhaps even in the present. There is methane that periodically appears in the Martian atmosphere, a gas which is associated with life on Earth. We know there is organic matter in some Martian rocks, and we know that some of the organic matter has an isotopic ratio of its carbon, which is suggestive of the isotopic ratio that is formed by biological processes. But there may be other explanations, and I suspect at a very minimum it will take carefully collected samples brought back to Earth to decide that question, and more likely it will actually take systematic exploration by science astronauts on the surface of Mars to answer that question.
Thank you, Jon. And also, I noticed that since beginning you have been involved into the many type of Earth Mars analog explorations, and you have a good expertise knowledge in the geology, mineralogy. So, so how those your knowledge, which is relevant to the geology, that have been impacted to the convert your experience in that Earth Mars analog and other activities, and then also how important to study that Earth Mars analog activities before we head into the Mars?
Well, I am biased, and I'll say I think it's very important. The important about Mars analog research is when we talk about an analog, we're talking about a yardstick that we can compare with what we find on Earth with what we find on Mars. And I'm looking for something here that I can use. I don't know. All right. When we want to measure something on Earth, we take a ruler, and that tells us both how similar something is and also how different it is. So if we find a shell on the beach, we can measure it as being 5 centimeters long And if we find a fossil of that shell somewhere else and it's 10 centimeters long, this both helps us understand the similarity and the difference. And when we study analogues on Earth, that helps us understand both the similarity between Earth and Mars and the difference. So one example would be the Horton crater on Devon Island, where I spent nearly 2 months a number of years ago. That's a big impact crater, 20 kilometers across. And in many ways, it resembles large impact craters that we see on Mars. It's an area that has permafrost, which we have frozen ground, with which we can compare between Earth and Mars. But in other ways, it's very different. So, for example, the rocks at Horton crater, they're all limestones, which we don't find on Mars. So we can see both the similarities and the differences, and both are important. If we go to Ladakh, I mean, in many ways, Ladakh has many similarities with early Mars. Early Mars had a denser atmosphere than we have as now, but probably less dense than the pressure on Earth. You know, Ladakh, some of the areas have only half the air pressure that you would have sitting in Mumbai or Delhi or even in Canberra, where I am. So hot springs, we see hot springs in Ladakh, and we see hot spring deposits on Mars. And of course, because the air pressure is lower, they boil at a much lower temperature. They don't boil at 100 degrees. Water boils at about 84 degrees. There are other things. There's salt lakes there, which have the same sort of salts that we see in Martian salt deposits. And so there are a lot of similarities there, not between modern Mars. The moon is more like modern Mars than Ladakh is, but like ancient Mars. Ancient Mars, 4.5 billion years ago, which is the time when, Earth and Mars were very, very similar. They all had atmospheres, they all had oceans, they all had volcanoes and hydrothermal systems, they all had organic molecules, and perhaps life as well. We know Earth had life 4 billion years ago. Maybe Mars did.
So if the Mars had a life before 4 billion years ago, so is there any probability to preserve those things as fossils, like I don't know, as an example, like we have igneous sediments and metamorphic type of rock. So the compositions of the rocks and the minerals over there is enough to become a fossilization process, any kind of.
Well, we have fossils on Earth that are 3.5 billion years old, of stromatolites, little columns formed by microbial colonies, cyanobacteria. So we can find fossils in rocks that are almost that old on Earth, and another 500 million years should make much difference. Also on Mars, we didn't have plate tectonics to the same extent we had here on Earth. So rocks should be less metamorphosed, less cooked on Mars, well, for the most part, than they are here. And if we can find stromatolites on Earth in rocks 3.5 billion years ago, and fossils and chemical traces, we should be able to find them on Mars as well. And in fact, just hold your thoughts for 1 minute. I'll be back.
Dear students, it's your time. If you have further more questions, this is very interesting session because before we move into the lunar samples and other analogs in the evening time on today. So we have something like very interesting session which is relevant to meteoritics and the Mars sample return mission. Don't worry, we have another 2 simplified mission because I know that this is going to be a little bit complicated. Maybe it's advanced to some of our young students. For that case, I'm going to simplify every sessions by using the astrobiology and paleontology sessions in the upcoming future. So, yes, John.
Yeah, sorry, I actually have a sample of one of those stromatolites, and I thought I could find it, but I couldn't. It's somewhere in my collection. But in a hurry, trying to show it to your people, I couldn't find it. Maybe next time.
Yeah, we'll try next time.
Well, I've always been interested in geology, the history of our Earth. I've always been interested in space exploration. And so those two things combined also make me interested in the search for life off Earth.
I see. That sounds very interesting. And so what is the best advice that you can just give it to the young people, like if they are looking for become astrobiologists, like space scientists or analog astronaut? So what will be the best advice with your experience?
Well, I think it's important, first of all, to gain good qualifications in a relevant field. Now, astrobiology is very diverse. So people who are biologists will come from it, will look at biological questions. People who are geologists will look at it from a geological perspective. Oh, actually, I will do that. So just going back, this is a stromatolite. This is a young stromatolite. But we do find these in the very ancient rocks in the Pilbara 3.5 billion years ago, and they're pretty good evidence for life on Earth. Okay. How do people become astrobiologists? Well, I said, first of all, become a good biologist, become a good geologist. If you're an engineer, become a good engineer. We need good engineers to develop the tools that will sample Mars, be they robotic tools or tools that astronauts use, handheld tools, drill rigs. If your skills lie in medicine, the whole question of planetary protection involves understanding medical science, mathematics. A lot of life biological questions have a mathematical basis, so you can approach it there. So whatever your skills, whatever your interests are, there can be a facet of that, an aspect of that you can apply to astrobiology. So do a degree in one of those subjects. It'd be good to work in the field, practical experience. Medically, work in a hospital. If you're a biologist, work as a biologist. If you're a geologist, go out and find mineral deposits. Do postgraduate studies. There are people, there are universities in India that offer postgraduate degrees, planetary science and astrobiology. There's ones overseas. There are Indian people all over the world studying these. So do one of those. And I don't do astrobiology or planetary science all the time. Right? My paid job for many years was looking at groundwater for the government. But I did these things on the side. So even if you don't get a job in astrobiology, doesn't mean to say that you can't still do useful work in the field. You've got to eat first, right? And you can still find aspects of your work that you can apply to astrobiology. Work at it part-time, work with it in groups, like Protoplanet, the company which is we're going to Ladakh with. If you can't get paid in it, do it for fun.
Yeah.
Because it will be fun anyway, whether you get paid for or not.
Like exactly true. Like I noticed that Protoplanet and the Earth-Mars analog missions in Ladakh. So that's inspire even more the South Asian country because of the knowledge in astrobiology. It's a very lack. And I had to just pass special thanks for the UNU and the Siddharth. And is doing some incredible work to providing outreach work and the educational, which is relevant to the geology, the astrobiology, and that's motivating for our even science, even our young students.
Yeah. And be prepared to move. I mean, it's a growing field in India, planetary science and astrobiology. There are opportunities overseas. I'm not sure if America is a good place to go at the moment, but certainly in Europe, in many parts of other parts of Asia, in Japan, in China, there are opportunities as well. So, keep a wide horizon, and who knows where you might end up.
That is exactly true. And dear student, if you have further question, make sure to drop into our WhatsApp group. Then I can just pass into our Professor Jonathan Clarke. So I'm going to wind up the today's session because make sure to remember, dear students, today evening also you have another sessions. So dear Professor Jonathan Clarke, and I would like to, yes, I think like before I wind up, I noticed Hasindu have been just raised a hand. Yes, Hasindu, go ahead, ask your question.
Sir, how meteorites named and who approves names?
Okay. Meteorites have to be found. Sometimes people see them falling from the sky, but usually they are found. There are a whole range of tests that have to be done on them to show they are meteorites and not terrestrial rocks. These are published. Usually it's done through a university or through a museum. So if you find a rock you think is a meteorite, take it to, pardon me, to a university or a museum with the appropriate skills. In Australia, all meteorites if found belong to the museum of the state they're found in. People are not allowed to have private collections of meteorites. Other countries have different rules. There is an international committee of meteorite experts, and they also they review submitted samples and provide a review process to determine whether these are truly meteorites or not. I hope that answers your question.
Thank you, sir.
Okay, thanks for the Asindu for the nice section, and thank you for the Professor Jonathan Clarke for answering it. So now I'm going to wind up the sessions. Dear Professor Jonathan Clarke, I would like to pass our greeting and special gratitude to you.
Thank you.
Because every time you motivate most of Sri Lankan students and providing such excellent education and outreach which is relevant to the astrobiology and even the geology. And you are a very humble person since beginning. I know that last 5 years we are closely working with some different activity, and at the end I want to wishing you very all the best for the Ladakh mission in the future.
Thank you. Thank you. And see you next time. Goodbye.
Yeah, see